the last control source that we need to talk about is the current controlled current source. So, ideally what comment can you make about the input resistance of a current controlled current source? Ideally Ri must be 0. What about the output resistance? Infinite. And so, when you say I have a current controlled current source, the only number that you need to specify is the gain, and for reasons that will become apparent going forward, let us first try and attempt to realize a controlled current source with an incremental gain of 1, right. So, I out by I in must be equal to 1. All right. So, basically we are saying here we have a current I in, okay. I need to generate a current I out which is the same as I in. Okay, again we go through the same process that we have done for the previous current sources, namely first think about what to do and then we figure out how to do it. All right. So, if you are in a lab and you want to generate another current which is the same as I in, what will you do? What all would you need? We need a variable current source. Okay. So, let us say we have a variable current source. All right. So, this is variable. Okay. Now, what are we going to do? And remember that a current source must never be opened, just like how a voltage source must never be shorted, right. Okay. All right. So, we have this variable current source. So, what are we going to do? How do we make sure that this current Ix is the same as I in? Of what? And how do we take the difference? Yeah. So, we want to measure the we have seen this before in the context of biasing transistors. So, if we want to make sure that Ix is the same as I in, what do? We want to find the difference, and then so what physical principle will we use to find the difference between two currents? KCL. So, basically we join the two and we can monitor the potential of node X, correct. So, if Vx goes up, what does it mean? It means that Ix is too much, and therefore, what must you do? Must reduce Ix. All right. And on the other hand, if Vx is going down, it means that the current pumped into the node is too little compared to the current that is being, or the charge being pushed into the node is smaller than the charge that is being pulled out of the node. As a result, the potential of the node reduces. So, Ix must fall. I mean, so if Vx is falling, it means that I in is too much, or in other words, Ix is too little, and therefore, Ix must be increased. All right. The only circumstance when when Ix is equal to I in, what will happen? The potential of Vx will not change, correct. But recall that all these signals that we are talking about are incremental signals. In the incremental network, you can never have a constant voltage, correct. So, that any constant voltage must only be 0, right. In the real network, you can have a constant voltage, but when you go from there to an incremental one, any constant voltage becomes 0. So, basically what we must do? We must compare the potential of X with 0, right. It must be a constant, that constant must be 0. So, we compare the potential of Vx with respect to ground, and if Vx increases, Ix must decrease and vice versa, correct. So, in other words, Ix must be a current which is proportional to, it is controlled by Vx, the constant of proportionality must be some conductance. What comment can we make about the sign of Gm? Yes, negative. Why? Because if Vx is going up, Ix must fall down. So, this is basically minus Gm times Vx, alright, which to aid you I am going to write this as Gm times 0 minus Vx, and now can you identify the transistor for me? Which is the term, which is the transistor? Pardon? Gate is grounded, very good. X is the source. This is alright, and therefore, the incremental picture basically looks like this. This is I0, this is I in, alright, and what do you call, ideally what should that Gm be? Ideally you like that Gm to be infinite. So, therefore, what comment can you make about the, if Gm tends to infinity, what comment can you make about the incremental potential of node X? Vx will tend to 0. So, what comment can you make about the input resistance? Why? Why is it 0? Yeah, well, you are pushing in current, that potential of that node is not changing at all. So, which implies that the input resistance is 0, correct. What comment can you make about the output resistance? Where is the output? This is I0, alright, and what comment can you make about the output resistance? We did this before. Yes? Why? No, it is infinite, that is correct, but why? Open circuit where? Okay. So, basically I hope you are all able to see this, right. It is apparent that if you form the incremental circuit here, what happens to the what happens to I in? Open circuit. Remember, I mean, if you are confused, the easiest thing is to put a V test and then measure the I test. So, obviously, if I in is an open circuit, then, well, whatever you V test you put here, there is no current flowing, correct, and therefore, I test is 0. So, therefore, output resistance is infinite. And what is I0 by I in? I think we call this I out by I in must be 1. All right. Okay. Now, if I draw the picture in a slightly different way, all right. So, now before I do that, now what comment can I make if the source is not, current source is not ideal, but has some source resistance Rs? What is I out? Okay. So, if Gm is infinite, what comment can we make about I out? It does not change. Why? Well, the incremental voltage at X is 0. So, the current flowing through Rs is 0. So, all the current I in flows through the transistor into the drain. So, basically I out by I in is 1. All right. So, this is this is simply current controlled current source is it's basically taking a poor current source and making it look like a. Now, what is the point in having a current controlled current source? What is this? I mean, why do we? Why do we? If I out is the same as I in, why bother having a current controlled current source? Why don't we just take that that input current and connect it to the output of the wire? Why do we need this whole transistor and all that? The idea behind using a current controlled current source is that it can take a bad current source. What's a bad current source? Yeah, a bad current source is one whose output resistance is not infinite, it's finite. Okay. So, if you connect it to, if you connected a bad current source to a load, ideally you would expect that all the current provided by the current source must go in through the load. But unfortunately, because the current source is bad and it's got some internal impedance of its own, all right, okay, all the current will not flow, only a fraction of it will flow through the load, correct? And this is like pretty much like having to pay a bribe, you understand, right? You need to get a big loan from a bank, right? Of course, your financials are all very, very shaky, all right. But if you say, I'll give you you go to the manager and say, I'll give you, say 10% of the money. That's like poor output impedance, right? Okay, all right. So if more money is there, you lose. He gets a bigger cut, right? It's only a fraction of that current that flows through the recipient. The other 10% is lost. Okay, all right. So, the current control current source job is to basically make is to isolate. You can take a bad current source and make it look, or make it look great, right, and make it look like an ideal current source with an infinite output resistance. So, if I redraw this picture slightly differently, you will get an idea of why it is called what it is called. So, this is I in, this is Rs, this is a current source. I mean, let us say I push it into a load, all right. So, it is the same circuit except that I have inserted a load in the drain. I am sure this is familiar to all of you, correct. What is this? Here we see that the gate terminal of the transistor is common to both the input source and the load, and therefore, this is called the common gate. Okay. Another way of looking at it is, this is you, all right. So, you are not ideal current sources. This is the institute, right, okay, and this is the external world, So, this is the common gate amplifier. Okay. Now, again, you know, same old, same old. Of course, before we go there, we must figure out what happens when the transistor's GM is finite, right? What do we do? We've done this in multiple times before. So, what do we do? Well, Ix is nothing but GM minus GM times Vx, and so what comment can we make about Rin? So, let us say Rin is what? It's a no brainer, it is 1 over Vm, correct. Now, let us now put in a source, our friend, the source resistance. All right. So, what comment can you make about the I out by I in? The input resistance of the common gate amplifier is, as we just saw, what is it? 1 by Gm. So, how much of the current will IN will flow into the transistor now? Rs by Rs plus 1 over Gm, which can be rewritten as Gm Rs over 1 plus Gm Rs, okay, and that current will flow out. So, as you can see, the current gain is not exactly 1, it is Gm Rs by 1 plus Gm Rs. What comment can you make about the output resistance? With finite Gm? Okay, okay, let us apply V test and then find what I test is. Rs is there. We have, in fact, now this should ring a bell because we have done this analysis before. This is Rs, we are applying a V test here. What is I test? I test is 0. Why? Which one? So, in our model for the transistor, we assume that the drain source, the current in the drain is independent of the drain potential. So, basically, you know, you wiggle the drain, there is no change in the current, and therefore, I test is 0. So, the output resistance still remains infinite, even though the GM is finite. Okay, all right. So, R out is infinite. Now, what comment can we make about, therefore, when we say we want GM to be large, we know that we cannot make GM infinite, we can only make GM large. Now, the question is how large, and now we should be able, we should be in a position to answer that question. What is it? Very good. So, GM must be much larger than 1 over Rs, all right. Now, why do you think the current controlled, I mean, we said that the current controlled current source that we are going to attempt is going to have a incremental gain of 1. You know, why can't we make an incremental gain of 10? The reason is exactly analogous to what we saw in the which case? Voltage controlled voltage source, where also it was only possible to make an incremental gain of 1. The reason being, the transistor is a 3-terminal voltage controlled current source. Is that clear? All right. So, now the last thing to do is again come up with the real circuit. Again, we can pick our favorite bias scheme. I am picking something. I know it's terribly boring to keep picking the same thing all the time, but I am going to leave you to do some IRF. This is RL, this is VDD. All right, so I bias the transistor. Now what? What all should we do to make it a common gate amplifier? Capacitor at gate, right? Very good. What else? All right. That is RS. Okay. Now, if I remove this and this is Vi, let us say this is Rs, what comment can you make about the incremental voltage at the drain? So, another way of thinking about it, if you did not want to go back to the Norton equivalent, what is the incremental voltage there? What is the incremental voltage there? Yes? For infinite GM. 0. All right. So, what is the incremental current flowing there? Vi by Rs. So, where does that current flow? IRF is anyway open circuit in the incremental network. So, that will flow through the RL. So, what comment can you make about the incremental voltage at the load? Pardon? Vi times RL over Rs. Again, you can just look at it and then tell the answer.